And then you just put this on your belt.
Oh yeah, I'm amplified.
There you go. It's on, it's ready to go, your camera's good.
Here. All right, I'll just let it drop. Green light's not on yet. Excuse my stertorous coughing noises. I've been having nasty pollen allergies recently. It's a little bit better here than it is in Pennsylvania, but only better. I'm not actually sure it's better here. The pollen count's probably just as high, but the allergens are different. So much stuff I didn't get to in that talk yesterday. I ran out of time while I was still talking about history and didn't get to military operations. Oh well. Have to schedule a longer one next year, I guess. I do not see a green light. Possibly I am being oblivious. Okay. Very good then. I shall begin. I'm Eric Raymond, and you're not. And I'm here to talk about the 5 gates of the way, and this is in part an excerpt from a book I'm working on now called The Programmer's Way, A Guide to Right Mindset. Because one of the important things to know about programming, if you're learning it, or even if you're long past first learning it, is that mastery of programming rests on 2 very distinct pillars. One is knowledge of tools and techniques. You need to know things about compilers and interpreters and editors and version control systems and repository sites and all that technical impedimentia that we use these days. The other, far more important pillar of the mastery of programming is how your mind carves up the world. You have to approach problems in a particular way that finds the places to break them apart into pieces that you can specify. I think this is a skill that can be learned, but in general, we're very poor at teaching it, except by having people repeatedly bash their heads into the wall of writing code and seeing what kind of blood comes out. But I've long been interested in this aspect of the problem. Those of you who have read my last book, The Art of Unix Programming, will know that it is, in significant part, a book about mindset, about how you carve things apart. Well, I'm going further in this direction with this book. And one of the most interesting things I've learned about this is that a few years ago I read a paper called The Camel Has Two Humps. The paper was later withdrawn for what I consider suspiciously political reasons. They thought they had found a simple test question which would predict whether people would be able to make it in a computer science curriculum or a software engineering curriculum. The paper was later withdrawn, but I then found an earlier paper from 1988 that made essentially the same claim and seemed to be able to back it up with good statistics. And that is this. There's a basic concept, which I have pretentiously designated the first gate of the way, which if you can't get it, you're not going to survive a Programming 101 course. And that gate is sequential assignment. Sequential assignment is what happens when you have a variable over here, a container over here, and you put a value in it. And it then has that value, and this is an assignment that happens in time, synchronously with other things that are going on your computer. Very simple concept. I'm sure everybody in this room has no problem with it. According to the 1988 paper, only 2% of the general population is capable of passing the first gate. Now, I have my suspicions about this figure because it seems unreasonably low to me. I suspect that if the test population had been preferentially screened for like IQs above 110 or so, I suspect that 200 and 100 would go way, way up. But I don't know, and I'm not sure anybody else does either. So once I got my lunch hooks on this idea, I started thinking, what other barriers are there like this that are huge but unobvious to those of us who have already passed them? And I spent a fair amount of time discussing this with a group of very, very sharp friends of mine, one of whom is in this room. Say hi, Jason. What was that? And we eventually bashed out a list of what of the 5 gates of the way that I'm here to reveal to you. And why am I using pretentious Zen-style rhetoric? Well, because this is actually something I do a lot in my book, and I have a reason for it that's not just humorous. Zen rhetoric is the result of 3,000 years of people trying to figure out how to engineer in their students very delicate shifts in mindset. So, I mean, and they're good at doing it. They've been replicating their style of insight for a very long time, very successfully. So this is a toolkit I think I will co-opt as much of as possible. Now let's proceed to the second gate of the way. There was some dispute when we were discussing this over whether the second or third gates should be swapped in order. But I'm mostly satisfied with saying that the second gate of the way is recursion. The idea that a function can call itself before it has finished evaluating to compute a partial result, which is then passed back out to the calling instance. Many people, including a significant number of people who are programmers, don't get this. And again, it's one of those really simple things that we take for granted, but if you don't understand that this is actually difficult, you won't be able to grasp why there are so few skilled programmers in the world. I mean, we kind of tend to overestimate the number because we're an occupational peer group and we congregate around each other and we think the rest of the world is like us. It's not. We are not typical minds. And the interesting thing is the typical minds, the respect in which we are not typical minds, doesn't stop with the fact that we're a little higher in average IQ than the general population. There are other things going on that are probably more important, and the 5 gates are indicators of this. So, third gate. Boy, I'm going to run out of gates before I run out of time here. The third gate is pointers. Being able to distinguish between a value and a reference to a value, and reason about data structures that have pointers in them, linked lists, graphs, things like that. Some people never get this. It's not as easy as it looks once you've subsumed it into your thinking. And there was a time in early primitive programming languages when you didn't have to get this. Fortran didn't have pointers. Well, not explicitly, and it hid them in a lot of ways. So that's the third gate. The fourth gate, this is the first one where in a general audience of programmers, I sometimes discover people who have not passed it yet. And this is actually not unreasonable because many languages don't have first-class support for it. The fourth gate is closures. How many people here know what a closure is? Raise your hand if you know what a closure is. Okay, that's about what I expected. A lot of working programmers don't know what a closure is. It's actually a very handy thing to have in your toolkit if your language supports it. I'll explain why in a moment, but first I'll tell you what one is. A closure is a piece of code, essentially in most languages you can think of it as a function body, in which when you create the closure, it captures the value of some or of whatever variables it invokes from the environment at the time you created it. And then later, when you fire the closure, those variables that it capture have the value it had at the time it was created, not at the time it's fired. So this is actually very handy in things like GUI toolkits. We're constantly needing to do callbacks. Closures are a great tool if you have to program in callbacks. Those of you who know Lisp, and I wish there were more of you, will probably remember lambdas. Python also has lambdas, but only in a very crippled form. So that's closures. That's the fourth gate. The fifth gate is one that I think more people are familiar with, but I've listed it in that order because I think it's actually conceptually more difficult than closures. So it's harder to attain mastery of it. The fifth gate is concurrency. What happens when you have multiple processes or multiple threads of execution, and you have to mediate common access to shared data structures, and you have problems like asynchronous processes trashing data or reading incomplete data, needing locks, and then having to deal with issues like deadlocks and live locks. And that, again, many programmers never master this. It's becoming more necessary now because the end of Dennard scaling, what's often misrepresented as the end of Moore's law, the end of Dennard scaling means we don't have any choice but to do concurrency a lot. So those of you who have not mastered the fifth gate there, you're going to have to get there. Oh, thank you, sir. You're going to have to achieve that gate. So I've laid out the 5 gates for you. There are lots of things I can talk about related to this concept, but in order to know which things I should talk about that are related to it, I will now open the floor to questions. What would you like to know about the 5 gates? Can you think of a 6th gate? Do you think I might have them in the wrong order?
So, I think it was gates 2 and 3. You said you debated what order to put them in,
Yes,
and they were recursion and pointers.
recursion and pointers.
So to me, pointers feels easier than recursion. What was the debate there, and how did you land on that?
Because most people have to learn how to write recursive functions even in procedural languages. So I think usually that's the concept you encounter and master first. But I'm not sure about that. You might be right. The other side of that controversy might be correct. Anybody else want to weigh in on that?
I put pointers second and recursion third.
Yeah, maybe it's because I'm a Lisp head. I got recursion early.
I would say recursion before pointers.
Okay, so both sides of the debate are represented here. I think we can all grok at this point that it's not an easy call. Yeah, you there in the back.
I think closures cause recursion to kind of be a little bit more important than pointers because they cause
Well, yeah, but I'm not talking about importance. I'm talking about the order in which people pass these gates. So are you arguing with the order at this point?
I still think if you can't pass recursion, you're gonna trip really hard.
Of course. That's why the gates are a sequence. Recursion is the second gate. You don't get past that, you're going to have a lot of trouble with the others.
Yeah.
Now, you may not go hog wild on it the way us Lisp people do, but most people in procedural languages learn how to write recursion, even if it's not a technique they use a lot. Yes?
So, the first gate, just assigning a number of...
Sequential assignment, yes.
That's algebra. More than 2% of the world... Well, okay.
For the record, in case the microphone didn't pick that up, the question was, that first gate, sequential assignment, that's algebra. More than 2% of the world, oh, wait.
Not counting the third world. I think more than 2% of the
That may
second...
be wishful thinking.
So, one of the things I'm here to impress on you in this talk is how easy it is to fall into the typical mind fallacy. You're all geeks, and you probably all have IQs well north of 120. The world is a very different place from the point of view of a person with an IQ of 100. A very different place. And if you walk out of here understanding nothing else, try not to project your mental processes on other people too much, because you'll misestimate them if you do. Next.
Kind of coming from like a lot of small scale business software, I think data normalization almost feels like it might be a gate. I mean, it seems like people stick the wrong thing at the wrong level or don't, kind of factor their data right.
I have 45 years of experience as a programmer, and I'm not sure I know what data normalization is. Would you explain the concept you're driving at here?
Well, I mean, I guess in general, I'm sure CS has a definition, right? But the idea of, defining entities and, their attributes at the right level. So things like instantiation of entities,
Okay.
or types and templates and anything like that. It's all over the place in a lot of small scale business software.
You call that normalization. I just call it data structure design. Yeah, that's difficult. I don't know where it fits into the gates hierarchy, though. Certainly after pointers, because you really can't design data structures like that unless you got the conference of a reference, of a promise. And I don't know how I'd express that as a cognitive stance or a cognitive trick yet. But you've given me something to think about, and thank you, that's part of what I was after in interacting with an audience. So let's see, what should I go into next? Something related to the 5 gates. Or maybe I should pick a mindset essay from my book and see if I can remember enough to talk about it. Zigzag that way, zigzag this way. Anybody got any questions they haven't had answered? Yeah.
So I think you suggested this early in the talk that maybe this has something to do with the way things are taught. Maybe I sort of inferred something that wasn't there. But so my question is do you feel like these things are something that a lot more people could learn, but the way it's taught is difficult? So I struggled with pointers very early on.
Right.
And it was presented to me, I was learning C, so that was where I was learning it. And the person who was teaching it kept saying things like C is always pass by value. And that kind of clouded my understanding of what because I just couldn't get that.
So the question is, if I can digest your question down a little, I think you're trying to ask, is passing the gate something that can be conveyed by learning, or does it require talent?
Yeah.
Is there something innate and neurological that has to be going on for you to pass these gates? And the answer is, I don't know, and I'd really like to. I don't think this sort of thing has been investigated nearly enough. My guess, based on my history of interacting with a lot of bright programmers, is that if you're talented, you can pass these gates really quickly, and if you aren't, well, you may be able to get past them, but it's going to be hard and it's going to take you a long time. That's my guess. Do not take it as revealed wisdom. So, in general, this is something I think I've observed about programming. And let me talk about this, because it's a more general approach to these issues. There are two kinds of geniuses in the world and two kinds of skills. The two kinds of geniuses in the world are talent monsters and skill monsters. For example, let's take something unrelated to programming. If you are a music talent monster, you have excellent relative pitch, you have a good ear, you can improvise on the fly. There is something in your brain that just sinks into music and is able to fairly effortlessly generate it. If you are a talent monster, the barrier to becoming a musician is basically how quickly you can train your hands to make the correct motions for the instruments. Okay. On the other hand, if you are a skill monster, it's practice and learning and reinforcement all the way down. Your neurology isn't giving you a lot of help. You have to learn procedures and execute those procedures, and all your focus goes into learning those procedures and evaluating how well you can perform them. Is this a distinction that makes sense to everybody? No. Most things can be learned either by being a skill monster or a talent monster. This one's a little prominent for me because I'm at least a low-grade talent monster in music. And one of the things I learned fairly early is that talent monsters in any particular discipline can sort of smell each other. They can tell when they're in each other's presence. I got into a lot of jam sessions as a teenager that, it's a thing that shouldn't have happened. But apparently they could tell somehow, and sometimes I could tell too. So talent monsters can sometimes spot each other. Also, another skill that can be learned either way is physics. You have people who are talent monsters, like probably the most famous one is Richard Feynman, who had an uncanny, crazy neurological ability to visualize the behavior of physical systems and get it right. And on the other hand, you have people like Murray Gell-Mann, who have no physical intuition at all. They are skill monsters. For them, physics is all computation. It's all learning the procedures, evaluating the procedures, reasoning your way to a result. There's no native brain circuitry that's giving them a lot of help at all. Prose composition. There are talent monsters and there are skill monsters. The path to mastery is different depending on where you start. Now, what I believe in general about programming is that having a talent controls how fast you start, but it doesn't control where you end up. Having the neurological talent for programming helps you get from knowing nothing to being a reasonable journeyman programmer that people won't laugh at pretty fast. But there comes a point at which it has to start being skill mastery and keep being skill mastery. So maybe that's relevant to your question about whether this sort of thing can be learned. On the other hand, maybe I don't know anything and I'm typical minding. I'm still discovering what I think about this and trying to research it. So I won't pretend to know things that I don't. Any other questions? Yeah.
The data normalization, I think that could also be seen as data organization.
I think of it as data structure design.
Well, I'm not sure that it could. I'm not sure it's specifically data structure because those are behavioral. This is more of an organization, and I'm not sure that is a pillar as much as someone who's generating a goal. So I think it's funny, but if it was in there, I might argue that it is after assignment because why are you assigning something?
Wow, I'm going to go home and have to think about that. Okay, this is good. I'm really glad I gave this talk now. It's not a good talk unless you learn from your audience.
So is there a reason why the inclusion of closures, why there wouldn't be more like first-class functions included in that gate, or things like accepting a function as an input, returning a function as an input? Things like that.
I think closures can stand in for the whole functions as first-class objects thing.
Okay. And then I'm not quite sure where this would fit in, but a lot of code is sometimes trying to understand how people, when you talk about decomposing things, about how other people have decomposed things. Mm-hmm. And having to maybe adapt their attitudes or their mental model. Like if you thought of like entering into a project and people are already doing object-oriented programming, and you might have to adopt that mental decomposition. I'm not sure what you would call that, but.
I call that working in groups. In describing the 5 gates, I'm trying to focus on simple, characterizable barriers to gaining more mastery. There may be something that can be abstracted from data structure design that's that simple, but I don't know that there is yet.
So my question is, potential sixth gate is the art of appropriate abstraction. That is a skill that I think you would have to pass in order to be a proficient programmer.
So okay, I think I sort of agree with you, but what do you mean by abstraction?
Well, abstractions could take place in several areas. One would be like choosing the appropriate higher order functions or functional decomposition like the previous person was talking about. Others would be if you're using classes, how you're going to break the things out and separate out the areas of concern.
So I think we're just back to generalized problem decomposition here.
Sort of, yes.
Because the kind of abstraction you're thinking about, I don't think it can be cleanly separated from data modeling. Because your model of your data, your belief about how the entities in your conceptual universe behave, is going to drive the organization of your program and your functions and what abstractions you choose in writing the code. Relevant joke here. I used to tell people when I was asked why I liked programming, I would tell people it's the only way I know of to get paid for being an experimental epistemologist. So only about half of you laughed. So I will explain that an epistemologist is a specialist in the philosophy of how we know things and what it means to assert that we know something or have a justified belief or have a verified theory. And I've been maintaining for decades that every program is an exercise in applied epistemology, because it's a set of assertions about the grounds of your knowledge and the consequences of your knowledge. Okay, so we've talked about skill versus talent. I see at least a potential sixth gate, which I'm going to have to think about a lot. Where should we go from here? Okay, maps create mindset. This is a major theme in my book. It's hard to think about concepts, including and especially concepts in programming, if you don't have crisp terminology to describe them. So now I'm going to bounce off you, partly so you can be amused by these terms, partly so you can use them, and partly so that you might learn something from them. I've had a project for years of trying to notice what things programmers need names for that they don't have names for. And let me start out with a very simple one. I had a project, still have a project. It's called GPSD. It's probably on your laptop somewhere. It's a service daemon that you can run on any Unix machine. And it monitors the serial ports, any serial ports you tell it to on your machine. And if you happen to hook a GPS up to one of those serial ports, GPSD will notice, automatically figure out which of 14 protocols the GPS is speaking, sync to that protocol. It doesn't even care what baud rate the port is at. It can do auto-baud detection. It will detect the baud rate, detect the protocol type, sync to that GPS, and start shipping time and location reports in JSON in a documented format on a well-known port. And if there are ever mass-market driverless cars, my software will be reading the GPS in the car. It's in a lot of smartphones, too. One of the things I found that I had to do, at one point, I decided that the next big bite GPSD was going to take was a protocol a lot of you probably haven't ever heard of. It's called AIS, Marine AIS. And it's actually a requirement of law in most countries that if you have a boat or a ship, it has to have an AIS transponder, which is constantly squawking its identification, its location, its course and speed, and a bunch of other data. And the main purpose for this is automated collision avoidance. I decided that it would be a lot of fun if GPSD could also read marine AIS packets from marine AIS receivers. I didn't have a real reason for this. It just seemed like kind of a fun thing to do. But it turns out that the documentation for GPS for AIS is absolutely horrible. It was designed in fits and starts by multiple cabals of European bureaucrats. Trust me, you do not want to read the AIS standards. It will burn your brain. So in order to save my sanity and the sanity of all future GPSD developers, I wrote a document on how Marine IS actually works, not just as described in the standard. I wrote down what the standard said, but I also wrote down what has been observed on actual AIS transceivers. And this document it's got sufficiently good and sufficiently comprehensive that it's been used as the specification for 2 other projects at this point, besides GPSD. And this is what I came to think of as a ground truth document. A ground truth document is when you take an interface to a piece of hardware or a protocol or an entire class of hardware, and you describe exactly what it does and exactly how you verify that behavior by sending data at it or receiving data from it. Ground truth documents are not exactly program specifications, because they don't say how a receiver for the protocol or a client for the hardware should behave. They just say what it does. And the thing to not do in a ground truth document is tangle it up with what you intend your software to do. Don't do that. No wishes go into a ground truth document. No futures go into it. No expectations. Just what came out of the receiver, what came out of the disk drive, what came out of the whatever crazy hardware you're dealing with. And here's the important programming practice that goes with it. When you discover that an implementation does not match the ground truth document and you have to fix it, treat that as a bug that has to be fixed in the document first. Because if you don't, here's what's going to happen. You're going to end up with code that's riddled with documented and mostly undocumented assumptions about the hardware behaves, and you'll have a maintenance nightmare. On the other hand, if you have a ground truth document that is driving the code, you won't have a maintenance nightmare. You'll be able to go look at the ground truth and adjust the code accordingly. So there is a term and a practice that I think software developers need. Any questions? Has anybody actually written one of these? You have. Tell us about it. One of those documents, huh? He said, I can't. So, which I'm going to read as it's classified.
All I can say is that it defines signal processing and how that.
All I can say is it defines signal processing and how that works, and then the code has to implement the processing of that data.
Right. So yes, if there's code or code specifications in your ground truth document, you're doing it wrong. Just describe reality as it is. Another couple terms that I had to come up with when I noticed different ways that I was getting stuck while I was programming. There are two different pits you can fall into. Maybe there are more than two, but these are the two that stand out for me. There are two kinds of pits you can fall into when you program. One of them I call a stupid problem, and the other I call a finger trap. The characteristic of a stupid problem, this is how you know you've hit a stupid problem. You look at your code, and you look at the way it's behaving, and you think to yourself, it can't possibly be doing that. This can't be happening. When you have that moment of thinking, you know you're in a stupid problem when you spend a day or 2 days staring at 5 or 10 lines of code and trying to figure out how the fuck is it doing that. That's a stupid problem. When you are in a stupid problem, there is only one way out. Do not try to think your way out of this problem, because your puny brain is inadequate to thinking your way out. That is why you are stuck. That is how you are stupid. The only way out of a stupid problem is to instrument the fuck out of everything. Printfs galore. Capture and dump every single piece of the data flow you can get at, and keep staring at it until something in the instrumentation says, oh, that's funny. At some point, you will discover you are making an assumption about the code that wasn't true, and your puny brain failed to notice that. That's a stupid problem. This is distinct from a Chinese finger trap. That's a different kind of problem. A Chinese finger trap is one where you know what's going on, but you keep failing because you keep tripping over edge cases. The classic example of this is write a program, or write a piece of code that will take a block of pixels on a screen or in screen memory and copy it to a different northeast corner location, non-destructively. Well, that sounds really simple, doesn't it? Until you realize you have to deal with the situation where the source and copy rectangles overlap. One of the source or copy rectangles is partly off screen. What you find when you actually try to write BitBlit is that it's pyramiding edge cases upon pyramiding edge cases. You can't, the thing about finger traps is that you cannot solve them by instrumenting your way out. Because the problem isn't that you made an assumption that isn't true. The problem is you don't have a correct mental model. And getting a correct mental model is hard. The only way to fight your way out of a finger trap problem is to keep bashing at the mental model until you can actually fit it in your head. Notice how different this is from a stupid problem. And the main reason I'm giving you these two terms today is so that your brain can consciously grok that these are two different things. These are two different ways to go wrong. And you will save yourself a lot of pain and heartache if you learn to figure out early whether you're in a stupid problem or a finger trap. Any questions? How many of you are like laughing with pain inside because you recognize these? No questions? Well, then, let's see. Fun terminology. Okay. So let's talk about mindset and AI. There's a lot of worry these days that a lot of programmers are going to lose their jobs to ChatGPT-4 and its descendants. I have a principled reason for laughing at this fear. I don't entirely laugh at it because I do have a little fear that the lowest levels of the skill ladder that people climb as they become expert programmers, I don't know where the economics to support people in their learning years is going to be. That's actually a significant problem. But there's a reason why I'm sure that there will always be jobs for people who are very good at programming and programming design. And to explain this, I'm going to tell a story about the history of programming. The story begins back in those halcyon days when we had to program by changing plugs on patchboards. Well, that didn't last very long. People swiftly started programming by poking machine language into memory locations with toggle switches. Well, paper tape made it easier. And everybody said programming is really hard. And then along came the first symbolic assemblers. And everybody said, joy, joy, joy. We can abstract away all the messy details. Our problems are solved. Birds will sing. Unicorns will frolic. There will be rainbows. Is that what happened? No. And here's why not. Because we didn't apply symbolic assembler to produce easy solutions to problems at the scale that we could handle with bare machine language. Instead, the demand for complexity in programs increased. It increased to the point where, once again, we were at a level of mental challenge that we could just barely handle with assembler language. And then there were compilers. And everybody said, oh, good, we get to apply machine intelligence to programming and abstract away all the grotty details, and programming's going to be easy now, isn't it? Frolicking unicorns, rainbows, sweet songbirds. But alas, it was not to be. For once we got compilers, we didn't use those to make easy the problems that we could solve only with difficulty at assembler level. Instead, the demand for complexity went up. And why is this? Because when you're trying to get products to market, economics often rewards the people who are willing to pile up technical debt and complexity in order to get a product to market first. So you get this perpetual expansion of demand for just the amount of complexity that we can just barely handle. Okay, then we get the next phase, structured programming. Anybody remember structured programming? No more spaghetti code, clean loops, clean procedures, no nasty go-tos. And there were people, once again, who were saying, the complexity problem, it is solved. But alas, it was not to be, because the same thing happened again. I eventually discovered that this kind of phenomenon has been noticed before. As far back as the 1850s, there was a British economist named Jevons that said that noticed that when coal became cheaper, it didn't reduce the demand for coal. Instead, coal got substituted for other things. And when programming gets more efficient and cheaper, it doesn't become less complicated. Instead, demand for programming gets substituted for other things. Code gets substituted for other things like transporting physical goods. So we're always surfing the wavefront of the stuff we can just barely handle as human beings. And each layer of tools, I don't even have to go through the next couple of iterations. Object-oriented programming. There is a kind of a rage going on for formal verification and programming from machine-readable specifications. And now it's AI. But at each stage, what happens to programming is that we keep upping the complexity budget until, once again, we're at the ragged edge of what human beings and their tools in combination can handle. And what happens is the level of abstraction of the specifications keeps changing. But there's always a specification. There's always something that's composed by a human being, even if it's done through partly through prompts to a chat GPT. There's always a specification generated by a human being to respond to human concerns that has to be ground all the way down through the tool chain into executable code. But the stack getting infinitely thick doesn't change the fact that there's always a human driving one end of it. So that's why I think programming's never going to go away. Any questions?
Sorry, I don't have a fear that programming will go away. I have a fear of CFOs that think that they can replace 100 programmers with 10 kids out of college using ChatGPT.
So yeah, their companies will die and the market will learn better. Next question.
So how do you create reproducible builds when you use ChatGPT as a preprocessor?
Well, the question was, how do you get reproducible builds when you use ChatGPT as a preprocessor? And my answer is, well, that would be one of those problems, wouldn't it?
So you said that it would always be a human generating those specifications. You don't think the machines will ever be able to generate the next specification?
There is a possible future in which we get fully general artificial intelligence that is human equivalent in being agentic. That is not where we seem to be headed right now, and it's actually kind of funny since the AI risk, since people spent so many decades worrying about human equivalent systems with agency, and that's not what we got. LLMs are not that thing. They are wonderful mind amplifiers, but they are not minds. I suppose there's a possible future in which we actually have fully general AGI, but that's beyond my time horizon. At the point where we have to worry about that, we're all going to be uploaded into Computronium running in Matryoshka doll megastructures at that point. It's going to be a completely different universe. Other questions? Yeah.
So I used to kind of laugh also that the idea that programmers would be replaced by ChatGPT, but going back to the first gate, only 2% of people can get assignment So it's like I think there's a large majority of people that are like there's a lot of programmers who can be replaced by something like that. I mean, honestly, but something like that eventually. But one thing I wanted to ask about the gates in particular, and I guess about thinking about programming, is there's a practical application there that has to do with, I guess, in the case of tech managers and programmers too, who do or administer technical interviews. How do you identify someone who can pass the gates without acquiring particular knowledge?
Ooh, that's a good question.
Yeah, and what I had come up with, and some colleagues somewhat agree with me, is that at least the most general knowledge we can require that is not particular to what any institution does is, do they know Git? Because if they know Git, they can reason about a graph, they can reason about references, they can collaborate. Maybe they can reason about a content addressable file system. But it's like if they know the internals a little bit. But that's one of the general programming skills that you can use. But I was wondering if you had any other ones, or general skills at all, or general proxy tests at all that you would administer to see if someone could pass the gates.
I don't. But I gotta say, knowledge of Git is a pretty good touchstone. I agree. That's a good place to start. Since you mentioned version control systems, the next new terminology I'll give you is one that I learned from studying version control systems. I think this book I'm working on, I think what I'm about to tell you may be the most important thing I discovered while working on this book. Some years back, I have a quirk. It's a kink. I love writing domain-specific languages. Nothing makes me want to get out of bed in the morning and get to a keyboard more than a situation where there's this problem domain and a language-like thing could be done to it to make it easier to understand and manipulate. And I want to be the guy who designs that. I love doing that. And some years ago, I was a recent new Git user, and I noticed something very interesting. How many of you know about Git fast import streams? Not many of you. Okay, so this is new and interesting for you. The Git guys, being clever geeks, wanted to make it as easy as possible for people to export the content of other version control systems so that it could be turned into a Git repository. And they recognized that ain't nobody going to deal with Git internals directly. That's just way too painful. So they came up with this bright idea of a Git fast import stream. This is a thing you can do in Git. You can say with a repository, Git fast export, dump it to a file, and what you will get is a serialized representation of a set of objects and references between the objects, which losslessly describes the entire version history of the repository. And then you can feed that into Git fast import, and you get the live repository back. And the main thing they wanted this for was that so other people could write exporters from things like Subversion or CVS, and you would then take that export file and feed it into Git fast import, and hey presto, you have a Git repository. I looked at this, and I had this realization that what these people had done, inadvertently, accidentally, they had defined a standard interchange format for repository histories. And that's really cool. What can we do with that? And then I had this idea. If I write something that is a structure editor for this file format, knows how to manipulate the objects in the file and the linkages between the objects, implicitly, I have just written a repository history editor that can talk to multiple version control systems. That's kind of a cool idea. So I did it. The program's called RepoSurgeon. The first thing it learned how to do was read, edit, and write Git repositories. When it really got kind of interesting was when I decided that it needed to be able to read subversion repositories. Oh, I did not know what I was letting myself in for. It's only possible, if any of you have ever tried to do a conversion from a subversion repository, it's a pretty horrible thing, because there's this mismatch between the data models of subversion and Git that will land you in deep trouble if you don't have experience with it. But fortunately, subversion actually has its own equivalent of import streams. You can dump a subversion repository into a serialized dump format, which you can then feed to subversion and get the live repository again. So my problem of how do I read subversion repositories reduced to how do I parse a subversion dump stream and turn it into a sequence of Git-like objects? Stated that way, the problem sounds very simple. It ain't simple at all. The reason what I want to talk about right now is the precise reason it isn't simple. And to do this, the term I ended up using for the concept is semantic locality. A data representation has good semantic locality when you have one piece of that data set, all of the things that you need to know to interpret are really close by in terms of access or computation cost. A paradigmatic example of a data structure or a file format with excellent semantic locality is a Unix password file. It's a series of lines. Each line is a password entry. When you grab the line for a password entry, everything that you need to know about that account is right there. You don't have to go anywhere else. You don't have to seek forward or back through the file. It's all right there. That's good semantic locality. On the other hand, very poor semantic locality, version control systems. Because everything is intertwined with everything else. In particular, when you don't know what a revision is until you know what all its files are, and there's associated comment and timestamp metadata, and these things can be computationally far away. And where I really got my nose rubbed in this is subversion dump streams have this operation in them which says, copy this directory over there. And if you're trying to resolve that into what actually happened, you need to know what the state of the directory was at the time of the copy. But you can only know that by having accumulated the entire previous history of the repository and having all of that metadata in core. Worst possible semantic locality case. Image processing, good semantic locality. You can usually break it up into rectangular pieces, process the pieces, glue them back together. Databases, horrible semantic locality. Everything's intertangled with anything else. And in order to know what an item in a table means, you usually have to look at other tables. And they can be computationally and in terms of access time quite far away. Now, why is it important to know this distinction? Because it underlies a lot of disparate things that we don't normally think about as having common causes. Here's one. We've all grown up with the Unix philosophy rule of keeping your data file representations textual and simple. Well, it turns out that there's a hidden rule under that's more important. The actual rule that people are trying to get at with the Unix philosophy is keep the semantic locality of your representations good so that you can process them in small chunks and filter them. That's what's underneath. Keep it textual, keep it looking like a password file if you can, or like JSON or whatever. Another thing that the distinction underlies is how effectively can you apply concurrent programming and multiple cores to a problem. If it has good semantic locality, you're in great shape. You can break it into chunks, and the chunks don't have references to faraway chunks that you have to chase. On the other hand, poor semantic locality, you're screwed. You'll never know when you need to chase a faraway reference, or how far back or how forward in time the references actually go. So this is a thing to look at when you're evaluating data structure designs or looking at them. One of the questions to ask is, how tight can I get the semantic locality to be? Is there a way I can make that cost lower?